Hello everybody and welcome to chapter 24. Read sections 1 through 15 in your textbook. Become familiar with three-phase systems. In particular the Y and delta configurations. So if we have a single-phase generator, one complete shaft rotation 360 degrees of the AC generator provides a single sinusoidal waveform. The electrical generator converts mechanical energy to electrical energy. The basic parts of the generator is the stator, which is the stationary part, and the rotor, which is the moving part. And the moving part, the rotor, has the magnetic field source, while the stator contains the conductor where the EMF is induced, electromotive force. The induced voltage value at the ends of the stator depends on the magnetic field strength, the rate of the field change, and there's a lot of different functions there that is respective to the design of the AC generator. And we're not here to design generators, but we just want to understand at a high level how three-phase voltages are developed. Now the rotor, which isn't shown in this drawing, moves past each of the three coils to develop the sinusoidal voltage. Each coil is identical and they're spaced 120 degrees apart. And for the 60 Hertz system that we use in the US, the rotor in a 60 Hertz generator covers the full 360 degree rotation in 16.67 milliseconds, which is 1/60. The three-phase system delivers power to the grid efficiently. There's less material used in the cables because they're not as big diameter-wise if you didn't have three phases. And then that corresponds to lighter weight to support, and that goes towards the lower cost. The three-phase system also provides a smooth operation for large motors to start easily. And one important aspect is when the induced voltage is when one of them is at zero, the other two are around 87% of their positive or negative maximum values. The stator coils that generate the voltage, each phase will be 120 degrees apart or out of phase, providing a smooth delivery. Notice that the red sinusoidal waveform starts 120 degrees after the green starts, and the purple or blue one starts 120 degrees after the red one starts. So the respective sinusoidal expressions for the induced voltages of a three-phase generator equals the peak waveform times the sine times the angular velocity times time. And then we have a respective phase shift according to that 120 degrees out of phase with each other. And remember that the B is 120 degrees to the right, which means it's minus 120. Remember, shifts to the right of the origin are negative, and to the left are positive. So for phase C, it would be either a negative 240 degrees out of phase from the origin, or if we went on the left side of the origin, it would be 120 degrees positive. So here's some takeaways that we just discussed about the AC system that you can read in your leisure. Now here is the first of our three-phase configurations, the Y system. It's an upside-down Y, and some people call it a star also. So if you hear the word star, it's the same thing. And what we have here is the lines of the A line is coming into the load. The neutral, which is where they all meet, goes to the load, and we have a B line and a C line. The formulas for the Y system, the voltage of the line. And what we're talking about is line A to line B to C, line A to C. That's the line voltage. Line to line voltage might be a better way to say it. But the line voltage is equal to square root of 3 times the phase voltage. The phase voltage is the value of A to N, or B to N, or C to N. That's the phase voltage. So here's the vectors, given the magnitude and the angles. And here's the vectors for the line voltage, and here's the line to neutral voltage, the phase voltage. Sequencing. The sequence is determined by rotating the vectors. So here we have the vectors A, B, and C. And if we have a point P here and we rotate these vectors counterclockwise, we'll notice that A will hit this place first, then B, then C. So we would say that this is an ABC sequence. That's important because the phase sequence, if two phases are interchanged, the direction of the rotation of the motor would be reversed. And we're going to stick with the ABC sequences for our computations during this presentation. This graphic shows a delta connection. This is the generator going into a load. It's a delta configuration. We have A, B, and C. There's no neutral here on a delta system. The voltage of the line to line equals the voltage of the phase voltage. So we can see here A to B is the same as the voltage across that load, or that coil, I should say, in a generator. And here's the line vectors for the delta system. Now, there's no neutral connection, but there can be a center tap, and I want to show you that. Here, we have a 240, 120 volt system, and we do end up with a 208 voltage, which is an odd voltage. We have line to line of 240, and we have 120 volts here, and then we have a 208 volt here. So let's look at that. And we do use 208 volts in some devices, and I wanted to show you how we can get that. So if we have a center tap on one of these coils on the generator, between a line and that center tap is 120 volts. However, if we go outside that center tap and go to a line, we get 240 volts here. Or we get 208 volts to that center tap from another line that's outside this coil with the center tap. So I just wanted to show you that just in case you came across that. And here is a Y system that can give you 208 volts. If we have 208 volts from a line-to-line voltage here, I show you phase A to phase C, phase B to phase C, we have 208 volts. Now if we go from a line voltage to a neutral, then we get 120 volts. So let's go over our formulas here for the, if we're given a line voltage, but we're not given the phase voltage, we can compute that. The line voltage is equal, the phase voltage is equal to the line voltage divided by the square root of 3, which is 1.73, and we get 120 volts. So there's 4 possible connections between a generator and a load, and I have them listed right here. Y to Y, Y to delta, delta to Y, and delta to delta. Let's do some examples and get some experience here. What are the phase angles for an ABC sequence, a Y generator connected to a Y connected load? So phase A is at 0 degrees, B is at 120, and C is at positive. B is at negative 120 phase shift, and C is at positive 120 phase shift. And these slides match. This matches with our slides that we presented on slides 7 and 10. So next, what is the line-to-line voltage? The phase voltage line to neutral is given as 120 right here in all their phase angles. So remember that in a Y system, the voltage of the line equals the square root of 3 times the phase voltage. So if we multiply the phase voltage times square root of 3, we get 208 volts. And I circled those line voltages right here. To find the line currents, we first need to know what the total impedance is. So we what kind of load do we have? We have a balanced load. We have a 3 ohm resistor and a 4 ohm inductor, or inductive reactance. And it's the same on all of those. So the impedance, we use Pythagorean's theorem. Z equals square root of 3 squared plus 4 squared, and we get 5. And we get an angle 53 degrees, which is the inverse tangent of x sub L over R, 4 over 3. So the line current goes from here to here, and the phase current would be right here. So the line current equals the phase current for a Y system. They'd be the same. So the magnitudes of the currents on each line will be the same also, but the phase shift will be different as shown in our formulas. So here's our formulas here. We have A to N, which is our phase current, which is the same as the line current, equals 120 volts at a 0 degrees divided by 5 at 53. So I divide the magnitudes and subtract the angle. 0 minus 53 gives me minus 53. So if we do everything correctly, we have 24 amps and we have different phase shifting. Example 2, we have a Y connected generator and a delta connected load. We have an ABC sequence. So we're given a line voltage of 240 volts. So next we want to determine the phase currents through the load. So since the load's balanced, we expect the magnitudes to be the same, but a different phase shift. And I do the calculations on the next slide. So here's our slide here. We're dividing the line voltage divided by the impedance of the magnitude. And so we have 240 at 0 divided by 10 at 53.13, and we get 24 minus 53. And then I did that for each one of these. Next we want to compute the line current. So in the delta load. So we understand that in this balanced load, the line current, A to A, and are equal in magnitude. And the line current in the delta load is square root of 3 times the phase current. And we computed the phase current at 24 amps. So if we do the square root of 3 times 24, we get 41.52 amps. So we have 41.52 amps coming to here to A, and then we have a current here of 24, and a current here of 24, and a current here of 24 amps. And here I'm showing the line currents and the phase currents on that load. Example 3, we have a delta connected generator and a Y connected load. This load is capacitive. So we have R equals 6 ohms and X sub C equals 8. So if we did that in rectangular coordinates, it would be 6 minus J8. And then we could do Pythagorean's theorem and put it in polar coordinates here. We have 10 at minus 53 because it's a capacitive reactance. So VN, VA to N, equals the current, which is given at 2 amps. So we're given this, the current here, at 2 amps. Next, the line voltage is computed by square root of 3 times the phase voltage. And we get 34.6. So let's go over our calculations here. So I have 2 amps here. That's my current. And I multiply that times our total impedance. And so I have a value of 20 here. So our A to N voltage here is 20 volts. And what is our line voltage? So if we're given the phase voltage of 20, our line voltage is square root of 3 times the phase voltage, which is 34.6 volts. So that's all we have for Chapter 24 overview. Do problems 1, 5, and 7, 11, and see you next time. Bye-bye.